All right, so we start a new unit on circles today. As you can see, all these learning targets that we're going to try to get to over the next many weeks, getting lots of details of circles. But today we just start with the basics of like what makes up a circle, what do we know about them, and then there will be some formulas. You could always add that down here to just kind of keep track of them. Even today, there's going to be well, not so much today, maybe more so tomorrow, we'll look at like the standard form equation of a circle. For today, there's mostly just new vocabulary that you're going to see. So again, if you'd like to add any details for yourself down here, feel free to do that. And then later on, you can always use this little checklist to make sure you're understanding all those learning targets. But let's get started on 9.1 with this little launch first, and then we'll get to the actual notes, like the new vocabulary. So first thing we want to think about is that word similar, that similarity or similar that we worked on a couple of units ago. And it kind of keeps popping up because we saw it again when we talked a little bit about in Unit 6 as well. So it says complete the sentence, if polygons are similar then, and you could kind of complete it with lots of different ones. You could have actually done these on your own, but just to go through them all, there's a couple of ways that you could answer this. We could say something about all the corresponding angles must be congruent. Remember that angles always stayed the same when you had a similar figure, and this could be referring to any polygon that can be similar. And the other thing that we could write is about the sides. So we could say all corresponding, and I'm just abbreviating the word corresponding here, sides, remember they had to be proportional. That's why we worked with scale factors. We did not say that the side lengths were all the same. The corresponding sides were not congruent to each other. That only happens for congruent figures or congruent polygons. So that's a little bit starting to think about similarity again, because when we're about to get to circles, we're going to bring back this idea of similarity. But circles are not polygons. So we'll talk about why, again, it's not a polygon because of the curve. Like if you think of what it looks like, you can't have any curved pieces to it. And then just to kind of remind ourselves a little bit about what we were able to do with triangles before with similarity, remember that if you have two triangles and you're trying to show are they similar to each other, or what else can I do with it to find missing side lengths, I can use proportions and scale factors. This is just like a warm-up. If you wanted to review some of this, it's not required or anything. It shows us that all three angles, the corresponding angles, are congruent to each other. That's what these little rings around it are showing. In case it's hard to see that, I'll kind of make those a little bit more obvious. And then there's some side lengths provided. Again, very hard to see. This is a 3, this is a 4, and this is a 5. So this is showing us that this triangle, it's actually a Pythagorean triple, so it is going to be a right triangle, even though it's not labeled that way. But these three sides can then tell you that if this side is 12, how can I find the side XZ? And we know XZ corresponds with this side that has the 5. So you could write a proportion. We already know the two triangles are similar because of asimilarity. You just need two of those angles. And when I write a proportion, remember your proportion could be different than mine. I could do something like 3 over 12 because I'm matching up those corresponding sides. And then I could then use 5 is that corresponding side with x, let's say. And then solve that proportion. We get 3x equals 60. And when you solve here, we get 20. So you just found the length of XZ is 20 units, or just 20. Okay, so we did that kind of just to recap a little bit of what we've already done. And then now we get to one more idea about similarity. It says, is it possible to draw two squares that are not similar to each other? If you think back to even on the, I want to say the Unit 6 test, or it was maybe the Unit 7 test, there was some mention about squares and whether they're going to be similar. Same thing with rectangles or other shapes. Well, squares have all the same side lengths, and so if you try to compare two side lengths or two squares, the side lengths will be the same ratio. Like if I have a square that has all 4s and then another bigger square that has all 9s, that ratio is the same scale factor. And then the angles are always right angles. So squares are always similar to each other. No matter what, two squares are always going to be similar. So this is not possible because it said, is it possible? And then we're saying, nope, it's not possible, because when you have 4 right angles in a square, that means in every single square, so all the corresponding angles would be congruent. And once I have 4 congruent sides between the 2 squares that I'm working with, the corresponding side lengths would be proportional. The 4 congruent sides are congruent, so they're going to be corresponding sides proportional. So now for the actual notes that get us to understand what a circle is. Here's the definition. It says a circle is a set of all points in a plane that are equidistant from a given point, which is called the center of the circle. And you can tell from the picture here, we're going to draw all of these pieces in. We have a dot in the center here. That's called the center. We can usually give a capital letter to represent what that center is. So I'm going to use the capital letter P. And then for notation, you'll see a diagram of a circle with a dot in it, in the center, and then the capital letter next to it is the actual name of the center. So you know that this is talking about circle P. And then we can draw in a few other segments into here. So I'm going to draw a straight line from one end to the next, passing through this center. And you've probably seen this terminology before. I know they cover a little bit of this in middle school as well. This whole segment that I just drew in here is called a diameter. But if I only want to take half of the diameter from the center to one point on the actual circle, then this could be called a radius. I'm going to actually draw in another radius here. Just so you can have technically a bunch of radius. They're called radii when they're more than one. You can have lots of radius or radii drawn into a circle, and you can have lots of diameters drawn into a circle, as long as the diameter will always pass through the center and it'll go from one endpoint on the circle to another. So again, you could draw in so many different diameters, so many different radii, in case you needed to. And then we are going to just talk about this idea of similarity again, but with circles, just to understand circles a little bit better. The first thing we see here in this diagram is 2 circles. One of them is this large circle here, and it's labeled with a P as the center. And then this smaller one on the left here is P prime, because that is your transformed one. It is clearly, as you can tell, dilated. It's like shrunk, right, by a certain scale factor that we're going to figure out. Well, here's how you figure it out. You first, and then also, just to be clear, there's more than just a dilation here. It also moved. The center used to be here, but now the center is here. So it moved left and up a certain amount that we're going to need to count, because it says, can you describe all of the transformations that P went to P prime? So there's going to be 2 transformations here. We're going to start with, I'm going to start with the dilation first, because if you look at this radius, the radius is 2. Wherever you go from the center to any point on the circle, going up, down, left, or right, it's always 2 for that radius. So the original circle's radius was not 2. Let's see what it was. And again, you can go horizontal, up, down, or left to count it. So this is 1, 2, 3, 4, 5, 6 for the radius. Okay, so if the radius was 6, but now it's a 2, you can see how it's being like divided by 3. But we don't say that when we write scale factor. We're going to say scale factor is 1/3. So the first thing I have here is that it's dilated by a scale factor of 1/3. Or another way to write it is K equals 1/3. Right? We use that letter K often to represent that's the scale factor. Okay, and then the second dilation, and if you want to actually first draw a sample circle of a radius of 2, like saying that, oh, I just did, it did a dilation, it'll look like this. It's where you go up to the right, down, and left 2, because that's like the radius, and draw in that circle. This was technically still P prime because I changed it, but then I'm going to move it also left and to up. So now to count how far we're moving, going left, 1, 2, 3, 4, 5, 6, 7, 8 to the left. So we're translating. I didn't write the word translate, but you can add the word translate. Left 8, and then let's see how far we go up. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you're going up 9. Okay, so left 8 and up 9, those were the transformations. But when I compare these two circles, the first question it asks is, are they congruent, and why or why not? Now, circles don't technically have, if you think about corresponding side lengths or corresponding angles, we'll talk about how all circles are going to be 360 degrees all the way around a circle. You may hopefully already know that. No matter the size of that circle, we say it's 360 degrees around, because remember, if you think of like a clock, when we're working with like angles, that's the idea. So in that scenario, when you talk about corresponding angles being congruent, it's not technically an angle, but just talking about the angle measure or the arc. We're going to talk about arc measure and things like that, and it's how it's all 360 is the same. But here's what's not the same. Circles are not congruent because they have different diameters or radius. And of course, because of that, it makes the size of the circle different. And size being different is what makes something not congruent, right? We know that congruent shapes always have to have the exact same size or side lengths, which for triangles we saw that, and other shapes we saw that. With circles, we have to look at diameters or radius to help us see that clearly this was a radius of 6, this was a radius of 2. There are different sizes there for sure. But when we talk about this thing called similar, technically all circles are similar, just like squares were, because circles with themselves, just similarity means, remember, that the angles don't change. Well, since circles are still all 360 degrees around, they would still be similar because all that's changing is the scale factor of how to figure out your radius would change, right? We just found out a scale factor of 1/3, so dilations can happen with the scale factor being whatever your amount you're stretching or shrinking it. But yes, all circles are similar because there's a scale factor that dilates one circle onto the other. Okay, now on the back, we're just going to do a couple of quick definitions of more, like some of the words we already saw in this diagram. The only word or diagram I did not draw in was something called a chord, which you're going to see on the next page, and some examples of them. Then there's a whole practice you can work on as well, just to practice some of that vocabulary if you'd like to as well. Okay, so let's go to the back here. There's 3 definitions that we're going to fill in here. All of them are filled in. We just have to write down which word is it. So it talks about a segment whose endpoints lie on a circle. A lot of people read this and they think it's a diameter, right? But the diameter, technically, it's not wrong that the endpoints of a diameter are also on a circle, but a diameter has more detail to it, which is that it also needs to pass through the center of the circle. So this P to Q here, if you notice, those are 2 endpoints on a circle and a segment that's being created as a result. So segment PQ is an example of this, which is called a chord. I know it's spelled like not the word chord. It's CH, it's not chord. It is called chord, but it is spelled like this. So a chord is when the segment doesn't have to pass through the center, but it can. So technically AB is also considered a chord because it's 2 endpoints on a circle. But O is not, or O happens to be the center of this circle. It's not touching PQ, which is okay. PQ is also a chord. But OC is not a chord because it does not go to both points are not on endpoints of a circle. One of the points of OC are actually the center, which is where we're getting to the next one. A chord that contains the center of the circle is a diameter. Because remember, it has to touch both endpoints, but specifically it's also touching the circle, the center. So AB is the only diameter that's drawn in this diagram. I could draw others if I wanted to go passing through O, going like up and down. I could go diagonally. So many ways to draw many other diameters if I wanted to. And then there's a radius. The radius is a segment whose endpoints are the center of the circle and a point on the circle. So one of the endpoints has to be the center, wherever the center is labeled as, in this case O, and then the other point can be any other point. So we actually have a few examples here. I know a lot of people see OC, segment OC, and you can write them the other way around. You could write CO, it does not make a difference which one goes first, but technically OB and OA are also examples of radii. So even though it's part of the diameter, you can go one way to the right, one way to the left, that's still considered a radii. Okay, now if I wanted to connect O to Q or O to P, I know it's not done on the diagram. Technically, O to P would be a radius, OQ would be a radius, and I'm just going to write here that these are not on the diagram. But again, they could technically be connected if I needed to talk about more radii, or if I was asked, is segment OP a radius? Yes, it would be a radius because it's going from the center to a point on the circle. And that's pretty much it for the vocabulary. It's not brand new information today, like super new stuff, but a lot of the homework today will be a lot of practice of this new vocabulary. I know it's kind of repetitive. Homework is only the front page of the homework packet, so it's pretty short. You could finish before you go, and I may check it in tomorrow. Either way, you should complete that homework. And then there's some questions about radius and diameter as well, but your goal for today is to really understand all the new vocabulary and really make sure you could say what each thing is or identify what some diagrams, it's from the diagram, what are some different examples of chords, diameters, radius, what's the center, that sort of thing. So it's really just 4 new vocabulary words, these 3, and a center. All right, if you have questions, bring them tomorrow.